Have you ever looked at a map of the world and seen those scattered red triangles marking volcanoes? We tend to think of them as isolated giants, each with its own temper, its own timetable for eruption. But what if I told you that's not the whole story? What if these seemingly separate mountains of fire are part of a vast invisible network, a web of geological whispers that stretches across continents and beneath oceans? Imagine Yellowstone, the famous supervolcano in the heart of North America. We know it's a slumbering beast, its massive magma chamber breathing slowly beneath the beautiful geysers and hot springs. Now imagine a rumble from deep within Yellowstone. Not necessarily a full-blown eruption, but a significant shift, a geological sigh. What if that sigh didn't just stay in Wyoming? What if it traveled, silently and unseen, through the Earth's crust, like a message sent down a hidden wire? And what if, thousands of miles away, another volcano heard it? A volcano like Campi Flegrei in Italy or Mount Fuji in Japan. What if the whisper from Yellowstone was just enough to nudge that distant volcano over the edge, waking a dragon on the other side of the world? This isn't science fiction. This is the cutting edge of geology, a new understanding that is forcing us to rethink everything we thought we knew about volcanic activity. For decades, the prevailing theory was that most volcanoes operate independently. An eruption in Indonesia was just that, an event in Indonesia. But recent studies and increasingly sensitive seismic data are painting a very different picture. Scientists are starting to see patterns, subtle correlations between eruptions that are too coincidental to ignore. They're discovering that deep beneath our feet, the Earth's mantle isn't a uniform, molten sea. It's a complex system of currents and plumes, hotspots and channels. Think of it like the weather. A storm system that forms over the Atlantic doesn't just stay there. It's influenced by jet streams, ocean temperatures, and pressure systems thousands of miles away. It turns out the Earth's interior might behave in a similar way. A major geological event, like the slow filling of a magma chamber under Yellowstone, could change the pressure and stress dynamics across a vast section of a tectonic plate. This change in stress doesn't have to be huge. It can be incredibly subtle, a tiny nudge on a geological scale. But for a volcano that's already primed and ready to erupt, a volcano that's been building pressure for centuries, that tiny nudge could be the final straw. It's like a row of dominoes, but instead of being lined up on a table, they're scattered across the globe, connected by invisible forces. The fall of one doesn't guarantee the fall of the next, but it dramatically increases the probability. Let's dive deeper into how this could work. One of the key concepts here is something called dynamic triggering. When a massive earthquake happens, it sends seismic waves racing around the planet. We've known for a while that these powerful waves can trigger smaller aftershocks and even small eruptions in volcanoes that are very close by. But dynamic triggering on a global scale is a much bigger idea. The theory is that the low-frequency waves from a major geological event, whether it's a huge earthquake or a significant magmatic shift under a supervolcano, can travel much farther than we thought and still carry enough energy to affect distant volcanic systems. These waves can slosh magma around in a chamber miles below the surface, shake loose a geological plug that's been holding back an eruption, or change the pressure in the delicate plumbing of a volcanic system. Consider the 2004 Sumatra-Andaman earthquake, the one that caused the devastating Indian Ocean tsunami. In the months and years that followed, geologists noted a surprising uptick in volcanic activity in seemingly unrelated regions. Was it just a coincidence? Or did that massive rupture, which literally changed the shape of the seafloor, send out a planetary-scale stress signal that pushed other systems closer to their breaking point? The evidence is mounting that it's the latter. Now, let's bring it back to Yellowstone. Yellowstone isn't just any volcano. It's a supervolcano, meaning its past eruptions were thousands of times larger than anything in recorded history. The magma chamber beneath it is colossal, a sprawling reservoir of molten rock that influences the geology of the entire North American continent. If Yellowstone were to experience a major magmatic event, not necessarily a surface eruption, but a large-scale movement or intrusion of magma deep below, the resulting shift in stress on the North American plate would be immense. This stress wouldn't just stop at the edge of the park, it would propagate outwards. Could it reach the volcanic systems along the west coast, like Mount Rainier or Mount St. Helens? Almost certainly. Could it travel further, across the Pacific, influencing the notoriously active Ring of Fire? This is the question that keeps volcanologists up at night. The Ring of Fire is a 25,000-mile-long chain of volcanoes and seismic activity that circles the Pacific Ocean. It's the most geologically active region on Earth. Imagine the stress from a Yellowstone event rippling through the Pacific Plate, like a wave crossing a pond. It encounters volcanoes in Alaska, Japan, the Philippines, Indonesia, and all the way down to New Zealand and South America. Each of these volcanoes is in a different state of readiness. Some are dormant, some are quietly building pressure. The incoming stress wave from Yellowstone acts as a kind of audit, testing the stability of each one. For the ones already on a hair trigger, it could be the final push. This isn't about one eruption setting off a simultaneous global catastrophe. It's more like a geological whisper that starts a chain reaction, a cascade of events that could unfold over months or even years. An event at Yellowstone could be followed weeks later by an eruption in Japan, then months later by activity in the Andes. To an observer without the right data, they would look like separate, unrelated events. But to scientists who can read the deep seismic language of our planet, they would be connected chapters in the same story. So what are we doing about this? Well, the first step is listening. Our ability to monitor the Earth has exploded in recent decades. We have a global network of seismometers, GPS stations that can detect ground movement as small as a few millimeters, and satellites that use radar to map changes in the Earth's surface. We're gathering an unprecedented amount of data, creating a real-time health chart for our planet. Scientists are using this data, combined with powerful computer models, to simulate how stress travels through the Earth's crust. They can model a hypothetical event at Yellowstone and watch how the resulting stress waves propagate across the globe, identifying which volcanic regions are most likely to be affected. This is incredibly complex work. It's like trying to predict the exact path of every single raindrop in a hurricane. But with every new piece of data, every refinement to the models, the picture becomes a little clearer. This research isn't about fear-mongering, it's about preparedness. Understanding these deep connections is crucial for assessing global risk. If we know that a major shift at one supervolcano could increase the likelihood of eruptions elsewhere, we can improve our monitoring and our warning systems. It changes the equation from simply watching individual volcanoes to monitoring a global, interconnected system. This emerging science fundamentally changes our relationship with the planet. It reminds us that the ground beneath our feet is not static. It is a living, breathing system of incredible power and complexity. The forces that create beautiful islands and majestic mountains can also unleash unimaginable destruction. The story of our planet is a story of constant change, of hidden connections and epic forces playing out over geological time. And we are just beginning to learn its language, to decipher the whispers that travel through the invisible web beneath our feet. Thank you so much for joining me on this deep dive into the hidden world of volcanoes. If you found this as fascinating as I do, please hit that like button and subscribe for more explorations into the amazing science of our world. Let me know in the comments which geological mystery you'd like me to explore next. Stay curious, and I'll see you in the next video.